Hello everyone, today we will talk about bias formula. So the conditional probabilities. Definition formula is often useful under the following form. P of A intersected B equals P of A knowing B times P of B if P of B is strictly positive, of course. And this is, like we saw, the formula P of A knowing B equals P of A intersected B divided by P B. The following proposition is fundamental. We recall that a sequence of events bi, a finite sequence of events with E in n, in more precisely in 1n. Or we can also look at the not finite sequence. This sequence is called a partition of omega if bi intersecting bj dj is equal to the void set for all I different not equal to j, and if we have the union of the set being equal to the space. Each little omega, each element of our space, is then exactly in one of the bi. It belongs to one of the bi. To exactly one of the bi. The proposition is the total probabilities formula. For any event A and B, with P of B being strictly greater than 0 and strictly smaller than 1, we have, because if it is equal to 1 it is irrelevant, we won't even divide by P of B, there will be nothing. And so the formula is as follows. It is P of A is then equal to P of A knowing B times P of B plus P of A knowing the complementary of B times the probability of the complementary, the contrary of B. The event of B not occurring. In a more general scenario, if our sequence is a finite partition or countable of omega with P the probability of any set of our sequence belonging to 0, 1 excluded for all I in big I, then P of A is equal to the sum of our I, the sum of the probability of A knowing bi times the probability of bi. This is the formula, the total probabilities formula. We have this formula. This is when we have two events, and we also have this formula for a broader case scenario, or more events. Scenario where we have more events. So now let's prove this proposition. Since the intersection of A and bi, these events are disjoints, mutually disjoints, as we saw, and the definition is A intersected with bi. If we intersect this with A, B, J, it gives us the void set as soon as provided I is different from J, we have that our sets are mutually different with, we take sets mutually different sets with also A equals the union of our sets. So it is a mutually different union. We look at the probability of A. Probability of A is the probability of the union, but we saw that the probability of the union is also the sum of the probability of variance, since we are mutually different, since P is the probability. So it gives us probability of A intersected the sum of the probability of A intersected with BI. And this is by using the formula for the two events case, we saw that this is also the sum of P of A knowing BI times P of BI. And we just proved the formula that is blue frame above. Now let's look at an example. We have two cases. We have not faked piece, an honest piece, two coins. We have two coins. And there is one who is honest, one who is fake. There is one with two different faces and one with two identical faces. This one has two identical faces. We take coins. We choose a random coin. We choose randomly a coin. And we throw it 3 times. What is the probability to obtain 3 times the same face of a coin? The probability to obtain the same face. Here we have F and F, and here we have, let's say, F and P, face P, face F, let's say, and here a face F and face F. So what is the probability to obtain 3 times the same face? To solve this problem, we think with conditions, looking at the chosen coin. That is to say, we apply the total probabilities formula for the events. For the events A, we obtain 3 times the face F, and B, we obtain B, the coin is honest. It is not fake. B1 and B2, the coin has 2 times the same side, has 2 identical sides, has two faces F. We then have P of A. Probability of obtaining 3 times the face F is the probability of obtaining 3 times the face F knowing that the coin is honest, plus the probability of obtaining 3 times the face F knowing that the coin is fake, that the coin has 2 faces F. And we must multiply. I forgot. Times P of B1 plus P of A knowing B2 times P of B2, which is 1/8 times 1/2 plus 1 times 1/2 is equal to 9/16. The probability of obtaining 3 times the face F knowing that the coin is honest, so we have only one face F, is 1 half times 1 half times 1 half, so it gives us 1/8. Probability of the coin being honest is 1 half because we have 2 coins, and the probability of opening 3 times the face F, knowing the coin has 2 faces F, so this is a fake coin, is of course always happening, so it is 1 times the probability of the coin having 2 faces F, which is 1 half. So at the end we have 1/16 plus 1 half, this is equal to 1/16 plus 8/16, it is 9/16. So the probability of opening 3 times the face F is 9/16, which is quite high. It's not very surprising since we have 1 coin that is fake. Now let's see another exercise. Mr. and Madam Nobody. They have 2 children. Boys or girls. The 4 possible cases on the sex of the children is the same. We have probability. So the first question is, what is the probability that the two children of Mr. and Nobody are boys? Being boys. Without knowing anything. First situation without knowing anything more than we already know. 2. Knowing that the elder is a boy. And C, knowing that one of the children at least is a boy. Two, let's say that we call the Nobodies family, but the parents are not there. It is a boy who answers the phone. What is the probability that 2 children, Nobody, are boys? Here we also add information in the families with a girl and a boy. It's the girl. It is the girl who answers the phone with a probability P. So solution. The fundamental space omega is boy or girl to the power 2. When an event is realized in omega, we have the pair W equal to W1 to omega 1 omega 2, omega equal to omega 1 omega 2, where omega 1 is the possible sex of the elder and omega 2 is the sex of the younger. So we have omega boy or girls, boy or girls for omega 1 and omega 2. The fundamental space has the uniform probability. We denote by A the event two children are boys. Of course, we have A equal we mean boys. So the probability of the two children being boys, this is P of A. This is the cardinal of A divided by the cardinal of omega, and this is 1 over half. Because there is one case where this happens, where boys, girl, boy, and girl. With here the elder on the left and the younger on the right. So 1 over 4. For B, the event where if we know that the elder is a boy, then the event we denote by B this event. B is the event the elder is a boy. We then have that B is the following set of events. It is the following realization. We have two possibilities. The elder is a boy. Sorry for this. The elder is a boy. The elder is a boy. Younger. The boy. The elder is a boy. And the younger is a girl. And so P of A knowing B, probability of two nobody children being boys, is probability knowing that knowing the elder is a boy is the probability of A knowing B, and so it is the probability of A intersecting B over probability of B. So the probability of the two children being boys knowing that the elder is a boy is equal to the cardinal of A intersecting B, because we have equal probability, over the cardinal of B, and this is equal to 1 over half. This is just looking at this set. We take this realization, we have 1 over half. Cardinal of B is 2. Cardinal of A inter B equal to 1, so we have 1 over 2. Now, if you want to look at the event C, one of the children at least is a boy. So the possibilities are as follows. We have boy, then boy, girl, and girl, boy. So 3 possibilities. Then P of A knowing C, the probability of the two children being boys, knowing that one of the children at least is a boy, which is the probability of A intersected C. Probability of C, it is, since we're working with uniform probability, it is cardinal of A intersected C over the cardinal of C, and it is 1 over 3, because we have only one occurrence where the two children are boys, and cardinal of C is equal to 3. Now, if you want to be very meticulous for the second question, you need to change the definition of the fundamental space and we're going to take, for instance, omega equals girl, boy times 1 half. the last element of the space of the description of omega, that is to say 1 and 2, represents the index of the children, or the child, answering to the phone. Here the fundamental space doesn't have the uniform probability, because we also have to take into account the probability P of a child answering the phone. We denote by D the event, it is a boy answers the phone. Answers the phone. According to the total probabilities formula, we have P of D equals P of D knowing girl times probability of girl plus probability of D knowing girl boy times the probability of girl boy, which plus the probability of D knowing boy girl times probability of boy girl plus the probability of girl boy probability of boy no probability of plus the probability of D knowing boy times the probability of boy, which is equal to 0 times 1 over 4 plus 1 minus P times 1 over 4 plus 1 minus P times 1 over 4 plus 1 times 1 over 4, which is equal to 1 minus P plus 1 minus P over 4 plus 1 over 4, which is equal to 3 minus 2P over 4. And we have also P of A inter D equals P of D intersected with boy equals probability of D knowing boy times probability of boy. This is equal to 1 over 4. So the probability of A knowing D is equal to the probability of A intersected with D over the probability of D, which is 1 over 3 minus 2P. We can observe that if P equals 1, then if P equals 1, P of A knowing D is equal to 1. In that case, if a boy answers, we are sure that there was no girl at home, otherwise she would have answered. If P equals 0, then probability of A knowing D is equal to 1/3. In that case, if a boy answers, we know that at least that there is at least one boy in the family, and we can verify the result of the question 1c, the question 1c the second time. So that's the end of this video. That's the end for today. In the next video, we're going to talk about the Bayes formula. So I hope you learned a lot of things, and I hope you're impatient to discover Bayes formula. See you soon.